Okay.
Hey,
Can one confirm? Can you hear me?
I can hear you.
Awesome.
Can everyone
Yeah.
hear?
So what'd you say?
I was asking if everyone else can hear. Okay, it's
Oh,
fine.
okay. Do I need to check the chat or something?
Yeah, you can check the chat.
Okay. Okay.
Yeah.
Yeah, I think let's just jump into it. I'm gonna share my screen.
All right.
Okay. Hi everyone. My name is Olamilekan Ibrahim, and I'm going to talk about how Butter.us handles recordings. So if you don't know what Butter is, I'm also going to let you know what Butter is and what we're trying to do. So just a quick introduction. I'm a software engineer. I lead the backend engineering team at Butter, and on the side, I love scuba diving, and I'm also a Muay Thai boxer. And yeah, let's dive into it. So we have a table of content here. The first thing we're going to be talking about is what Butter is. We're going to dive into WebRTC and the standard way of recording and why it's not going to work for Butter. Then we're going to jump into the client side implementation we actually started with, and pros and cons and some reasons why it didn't work for us and why we had to move to a server side implementation. Then we jump into the scaling challenges with that server-side implementation and also the solutions. Then the last point would be, other learnings and bonus points. So let's dive into it. So what is Butter anyway? So Butter is a platform that lets you effortlessly plan, run, and recap super engaging workshops, trainings, and meetings all in one place. So it's a suite of tools that includes video conferencing and helps you effortlessly plan your sessions, helps you run those sessions, and helps you recap those sessions. So what does that even mean anyway? So this is just a screenshot from Butter. So imagine you're trying to run a town hall meeting. So Butter is mostly for workshops, but imagine you want to run a town hall meeting and you have agendas. You want to plan agendas. So the first agenda here is a check-in. You have some flashcards and you want some music playing in the background. And you also have another agenda here with also flashcards and breakout groups. Then you have more agendas. Basically, you can plan your entire session beforehand. Then Butter also lets you run the session. So you can see that there are some users, on the screen. It's just like running a session on Zoom, but you have more features and more tools. And we're trying to take away the technical overload on the hands of workshop facilitators. So imagine you have a workshop and people are going to have to use a whiteboard or some kind of a Miro, and you also want to play some music and all that stuff. You would have to, you have to keep track of multiple tabs. So you have a tab that's running the actual video conferencing. Then you have another tab that's running Miro. Then you have another tab that's probably running like your whiteboard and every other platform you want to use. But what Butter is trying to do here is trying to bring everything into one of those, into one platform, so you don't have to move around. So that's basically what Butter is. And one other thing Butter helps you do is, it uses AI to give you the best meeting recaps you can ever get for a video conferencing platform. So now we're going to dive into WebRTC. I'm sure a lot of people know what WebRTC is, but if you don't know what WebRTC is, WebRTC basically means web real-time communication. So it's a technology that helps you transfer data, mostly video and audio data, between browsers. So you want to send data from one browser to another, but you don't want to have to send it to a server. You just want to send it directly. This is what WebRTC does. So all you need is some kind of server that helps you connect those two clients together. Once the two clients are connected, then you can start, sharing data between the both of them, peer to peer, and that's like the basics of what WebRTC is. And there are multiple architectures you can have with WebRTC, but these are the two most common ones you would usually see in different platforms. So the first one is the P2P architecture. So the P2P architecture basically means you have, all your clients connected together, and each client has their video and audio streams. So if I turn on my webcam and my microphone, I have my audio and my video stream, and I'm trying to send my audio and video stream to all my clients on that same call. So I'm going to send my audio and video stream to this client. I'm also going to send it to this client, and I'm also going to send it to this client. And at this point, you can already see that there will probably be some issues at some point when you try to have multiple people on the call. So let's say you have 100 people on that same call. You're going to have to be sending your stream to 100 different clients, which makes no sense. And this basically says that this architecture works when you have just two clients, two different people on the call, and it doesn't go above like 5, for instance. That brings us into the SFU architecture. There are different ones, but SFU and P2P are like the most common. So the SFU architecture is different and it helps people scale. So what it does is there's a server somewhere in the cloud, and everyone sends their stream to that server, and that server relays the stream to everyone else. So instead of you sending your stream to all the clients separately, you just send your stream to that server, and that server relays your stream to every other client instead of you just having to send it yourself individually to different clients. And the server acts like a air tower control, if you know air tower control in aviation. So it basically gets all the streams and redirects them to where they're supposed to go to. So it's not going to send you your own stream. It's sending like the stream of other users to you, and you can have multiple settings however you want it. So the SFU architecture is basically a way to scale WebRTC. And an example of an SFU server you can use is MediaSoup, and it's open source. So now let's dive into the standard way of recording in WebRTC. So let's say you have a meeting with about 6 people, 6 clients basically. So you have 6 computers connected on that call, and you're using an SFU or a selective forward unit or a media server basically. What you're trying to do here is you're sending the streams of each user to that server, and that server is basically relaying it to every other client, which is what's happening in this second image here. And what you do when you actually want to implement a recording feature with WebRTC, like the standard way of implementing a recording feature here is, since you're already getting the video streams from each of these clients, what you have to do is save those streams somewhere. Like you save the audio and video streams somewhere. So you know that at the end of the call, you have the audio and video stream for this user, you have the audio and video stream for this user, and you have it for every other user. So once you're done with the call, what you try to do is run the streams through a processing pipeline. So what you do in this processing pipeline is basically to try to fit those videos in a grid. So if you take a look at Zoom recordings, you see that, you know, if you look at recordings on Zoom, you see that all the videos are in a specific grid. And if there's a screen share stream, the media server also saves the screen share stream and shows the screen share at some point. So the processing here is basically going to, you know, combine those streams into a grid and play them at like the specific intervals in which they were, you know, played in the actual call. So that's basically how you get recordings. Then you upload it to S3 and you make it presentable to users. So if you're building a WebRTC platform, this is the usual way you would record. So why would this way not work for Butter? And that's because Butter's recording feature needs to be a full replay of the entire session, not just video streams. So if you take a look at Butter, you want to be able to we want to be able to make sure that our recordings is a full replay of everything that happened during the session. We don't want to miss out on, you know, some of the collaboration tools like Miro, Mural, whiteboards, flashcards, and etc. So imagine you run a session on Butter and everyone used Miro. So they were using Miro boards or whiteboards. And while editing the whiteboards, they were having different conversations. And imagine you implement a recording feature, and the recording feature only includes, you know, the video streams and the audio streams of those users. Meanwhile, you don't have an idea what was going on in the board. Then you start to miss out, you know, on the context of every single thing that happened during that session. So this is an example of how we want our recordings to look like. So this is the standard recording for WebRTC. So you have everyone's video streams, then you merge them together in a grid, and you get a recording. That's good. But what we want with Butter is we want to be able to get every single thing the way it happened in the session. So it's like you're watching a replay of how everything happened, how it played out. So this is just a screenshot of, you know, some users on the call. And this is a flashcard activity. So people here are just trying to select between a dog and a cat. So this is just all those activities need to be in our recordings. So now let's dive into the client-side implementation. So Butter can be run on a browser. So you just go to, you know, a web page and you go to the web page and you can join a session. You don't need to download a desktop app or something. So this is the browser-based implementation of recordings. So when a host decides to press a button to start a recording, so you're in a session and you press the button to start a recording, what happens is that we're getting the browser's tab stream with Get User Media API. So the Get User Media API is a browser API that lets you get the media from the user, basically. So you want to get specific media from the user. And the media we want to get in this scenario is the user's tab. So the user is already on the call, And what we wanted to do was, since we want to record what's going on in the session, the best way to record it is from a user's perspective, right? Then that was what we decided to do. So we are getting the browser stream with Get User Media API. Then what we are doing is we are recording the tab stream with Media Recorder, which is another API on your browser that you can use to record streams. Then we record it with Media Recorder API, and we upload it to AWS S3 in chunks. Mind you, this is all happening on the browser side, on the user's side. So we are recording the user's tab, and we are uploading it to AWS S3 in chunks. So why are we recording in chunks anyway? So we don't want to record the entire call in memory, because if you have a call that's running around like 3 hours or 4 hours, and each frame is really huge, and the video is getting really large, then you're basically recording every single thing in memory, and you start to cause lags for the user. Another thing we're trying to avoid by uploading in chunks is to avoid like really long upload times for larger recordings, because we don't want you to wait till the end of your call and then record the full thing, which is also going to take quite a lot of time. Then another thing we're trying to avoid is to keep some parts of the video in case there's a failure. So imagine we're recording the call, and maybe your computer crashed or something, and your call was supposed to last 60 minutes, but your computer crashed at the 45th minute. Then you lose the recording. But what we're trying to do here by uploading in chunks is so that you at least get the first 45 minutes that were recorded before your computer actually crashed. Then what we're doing after uploading these chunks to S3 is to use AWS Media Convert to concatenate all those chunks together and convert it to MP4. So we have let's say we have a call that's about 60 minutes, and each chunk is about 5 minutes. What we're trying to do is record each chunk, then combine all those chunks together to form one video, and then we convert the video to MP4. And at this point, it's presentable to users. But it sounds good, but it didn't really work for us, and I'll tell you why. So the first reason is unreliability. So we have possible recording loss due to some specific reasons. And the first one is users mistakenly closing tabs. So imagine you're running your session and you're also recording on the client side, and you mistakenly close the browser. I mean, the session is still running. People are still in the call. People are having different conversations. But then you mistakenly close your tab. Then it means you've lost the recording at that point. Another problem is browser crashes. Let's say the user is running about 100 tabs, and like the browser decides to crash at some point. You also lose the recording. That means it's unreliable. And we don't want unreliability on a platform like this, because recordings are actually one of the most important features when it comes to WebRTC or when it comes to video conferencing. Then another problem is bad internet connection. So imagine a user that has a bad internet connection, struggling to send video stream, also struggling to send audio stream. Then we are also trying to upload we are also trying to upload the recording chunks to S3. Then you start to eat a lot of the user's bandwidth. Then, and if the connection gets worse, then you probably even lose the recording at the end of the day. Then another problem is users using potato hardware. You can't really tell what kind of computers the users would use. And when they use like computers that don't meet specific requirements, then you start to also have the same reliability issues. So what we decided to do here was to move this implementation to the backend somehow. And this had a bit of a rabbit hole, but I'll try to shorten everything as we move forward. So what we had in mind was that, like our plan was that when a user starts a recording, we have an EC2 server somewhere, like it's an experiment. We have an EC2 server somewhere that receives the recording request. So let's say the EC2 server has some sort of express setup, basic Node.js express setup. It receives the recording request from the user, then it spins up a headful Chrome browser. And you might ask me why we're using a headful browser instead of a headless browser. So the difference between headful and headless is that headless is actually being run in a command line. So if you run a Chrome browser in a headless form, then you don't want to see a graphic user interface. You basically just want to run Chrome in the command line without any UI. So that's what a headless browser is. And most times what you use headless browsers for is for stuff like web scraping, or in fact, even writing tests. You can write end-to-end tests with headless browsers. But if you're spinning up a headful browser, that means you're also getting the graphic user interface. And it basically means you want to see the full UI. You want to see everything that's going on in the browser. So we spin up a helpful Chrome browser. Then the third point here would be to use a tool like Puppeteer. You can use Puppeteer or Selenium WebDriver, whatever tool you want. I think Cypress also works, but Cypress is mostly for writing tests. So you use Puppeteer to control, a Chrome tab, join the call anonymously. Then we want to also record the meeting in chunks and upload them to S3 the same way we did in the client side implementation here. So we're still using, get user media API, media recorder, but every single thing we're doing now is happening on the server rather than on the client side because of the reasons, because of all these reasons we mentioned here, because like users mistakenly closing tabs, browser crashes, bad internet connection, and potato hardware. Now we're dictating what hardware we are running it on, and we would not have, we would not have issues like bad internet connection or user errors basically. So this was our plan, and we actually tried implementing, and we ran into some issues. So it's going to get worse at some point. So some problems with that implementation. The first one is that servers don't have GUIs or monitors to receive video. And it makes sense, right? It doesn't make sense for like AWS to say they want to start adding monitors to all their servers, like their data centers having monitors. And it makes no sense. People are running servers remotely, and you don't really need a GUI from servers. And that was one of the initial problems we encountered while implementing something like this. So our plan was to spin up Chrome and record the Chrome browser, but the server we're trying to run on, an EC2 instance we're trying to run on, doesn't have a GUI, doesn't have a monitor. So how do we get that video? So what we did was to introduce XVFB, which is X-Frame Virtual Buffer. So it's kind of like a fake monitor on your server. So you're running a server and you're using XVFB, but XVFB runs in memory and it acts like a fake, it acts like some kind of a monitor on that server. So it's a virtual monitor basically. So we used XVFB to get the video streams from the browser, from Chrome browser as we needed it. Then we also had another issue where we weren't getting audio. In fact, after using XVFB to get the video, we also weren't getting audio, and we realized, I mean, it should have been common knowledge, but we realized servers don't have audio drivers either. So even if we end up recording videos with XVFB, we will not be able to get the audios because the servers, the EC2 instances, don't really have audio drivers. But what we did was to introduce Pulse Audio, which is a sound server, and we use it to get the audio streams from Chrome browser. So if you're running YouTube, if you're in a butter session and you're running YouTube and everyone is watching a YouTube video or everyone is speaking, we're actually going to get that audio stream through Pulse Audio. So another issue we encountered was scalability. And I think this was one of the biggest challenges that actually took more time. So now I'm going to walk you through, the scaling requirements and problems that we had at this current stage that I'm explaining. So the first requirement was that we want to be able to record any number of meetings at any given time. So we're not sure how many people we're not sure how many meetings will be running at a specific time. And we don't care how many meetings will be running at that specific time. But all we care about is that we want to be able to record any number of meetings at any given time. That was a requirement. Then the second requirement was that we wanted reliability. So we wanted something that actually worked and something we could rely on to give us the video that we actually want to get from those meetings. So reliability was our second requirement. Then another one was the cost. We didn't want something that was going to be too expensive, which was because we were a startup at the time. I think this was like 2 years ago. We were a startup and we're trying to save costs. We didn't want to spend too much on AWS for this feature. So we wanted something that wasn't expensive, so we don't fund Bezos mission to space anymore. So what we decided to do, another problem, some of the problems we had was Chrome being resource intensive. So when you spin up a Chrome browser on an EC2 instance that has 4 CPUs and I think about 8 gigs of RAM, I'm not sure. I think it was a T2X large, T2 2X large, I think, yeah. 4 CPUs and about 16 gigs of RAM. Chrome, once you spin up the Chrome browser, it's going to take about 80% of that CPU at least on start, which was quite a problem for us. Then another problem we realized was running multiple recordings on one EC2 instance will cause video FPS issues. So that means Chrome actually just wants the full resources on one computer, on one machine to itself. before we can actually, and this was just spinning up Chrome. We haven't even gone to a point, we haven't even gotten to the point where we are recording, and the WebRTC platform itself is taking its own CPU requirements, and the recording is taking its own CPU requirements. We are only talking about the Chrome's, resource requirements at this point. And it was too much because like trying to run 2 recordings on one EC2 instance was going to give us, video quality issues and audio crackling issues. And what we had to do, what we decided to do, and how we tackled scaling is what we're going to talk about now. So the first thing we did was to completely get rid of EC2 due to the startup time. So imagine a user tries to start a recording, and it takes about 2 to 4 minutes to start. Then you begin to have user experience issues. I mean, you're going to get the recording at the end of the day, but it's taking 2 to 4 minutes to start, which is going to be very confusing, especially on the user's perspective. Like, why do I have to wait for 2 minutes? There are lots of conversations you can have before that EC2 instance gets spun up. So another thing we decided to do was to Dockerize the solution and deploy it to AWS ECS. So we basically packaged all the dependencies we needed, like XVFB, Chrome, Puppeteer, and we had lots of system dependencies that I can't even list now because there's a lot of them. So we got all those dependencies, put them in a Docker image, then deployed it to ECS. And we decided to use ECS Fargate. So why ECS Fargate to start with? So ECS Fargate is actually comparable to something like Kubernetes. ECS basically is comparable to something like Kubernetes, but ECS Fargate feels like you're running a Lambda function, but the Lambda function has more resources and it doesn't have a time limit. We know that Lambda functions have a time limit of about 15 minutes, I think. Yeah, there's a time limit of about 15 minutes, but we are running Fargate, which is a little bit comparable to Lambda, but it has more resources. It can run Docker, and it has no timeouts. There's no time limit. You can run it for however long you want to, as long as you're paying Bezos. So another thing we decided to do was to isolate the recordings, since one of the problems we had was that multiple recordings in one machine was going to cause video quality issues. And we don't want to make recordings at the end of the day and present those recordings to users, and users are complaining about the video quality. You're seeing audio crackling issues or video FPS issues. We decided to isolate recordings to avoid issues like that. So that means for each recording, we're going to spin up a new ECS Fargate instance to handle it and shut down afterwards. So imagine a user decides to record a call, presses the button to record a call. We're going to spin up a new ECS Fargate instance to run, Chrome initial solution, Chrome, XVFB, joining the call as an anonymous user and recording. So the ECS instance is going to get spun up, and it's going to join the call. It's going to do the entire recording. Then once the user stops the recording, then we shut down the ECS instance. That was basically the plan at this point. And this also gives the recordings full CPU resources they need. So we've basically tried to figure out what EC2 resources we actually need to give for each recording, and that was about four CPUs, 4 vCPUs, and about 8 gigs of RAM or so. So we decided the amount we wanted to give to each recording, and we decided to isolate them. And this was the plan. This was the first part of how we tackled scaling, and it has its pros and cons, and we'll go through them. So for the pros, there's no dependency on the client side, and this was the issue we wanted to avoid in the first place. So we didn't want to run the recordings on the client side. We wanted to run it on the back end. So we have no dependency on the client side. Another one is that it's pay as you go. Since anytime a user tries to start a recording, we basically just spin up the ECS instance. ECS instance runs the recording for however long the meeting lasts, or until the facilitator stops the call. So it runs for however long they need it to run, and then it shuts down. And we're only paying AWS for however long that ECS instance was up. And we can decide to charge users like 2 times of the amount of paying AWS, for instance. And that just makes it simple. And another pro is that we have no joint recordings on one machines, so we don't end up having the video FPS or audio issues. So we're basically isolating them, as I've mentioned previously, and we try to make sure that we don't run into any of those video quality issues, because we have actually run into them in the past during our testing phases, and presenting videos like that to users would definitely cause churn. So we had to avoid problems like that. Then now we're going to discuss the cons. And the biggest con for us at this point was that it was taking about 1 minute to start a recording. So ECS Fargate, EC2 was taking about 2 to 4 minutes. Then we moved to ECS, and ECS Fargate is taking about 1 minute to start that recording. And to be very honest, and I think everyone will agree with me that like 1 minute is a very long time, especially for users waiting for recordings to start. 1 minute is actually a very long time. And then we know that it's not something we can escape. It's a hardware requirement. If you shut down your computer and you try to start it up, there's a downtime, there's a wait time for you to wait before the machine comes up. So it's a hardware requirement, and you have to just find a way to find a way around it, basically. So now this is the second part of how we tackled scaling. So the first thing we did was to make the ECS Fargate tasks reusable. So if you take a look at the previous implementation, what we decided to do was, when someone records a call, we run the ECS Fargate machine to actually go through the recording. Then once it's done, it shuts down afterwards. But what we decided to do in this part 2 was to make it reusable. So you can use it for multiple recordings, but not at the same time. So first of all, it can actually stay idle until it's assigned to a recording. So you can just spin it up and it just stays idle. And we have a mechanism that actually assigns recordings to it whenever someone tries to record a call. But we need to make sure that those tasks were reusable, and I'll get to that in a bit. So they can stay idle until they're assigned to a recording, and they can only record one meeting at once. So, and we still want to preserve that isolation we've been talking about since the beginning of the server-side implementation. So we're trying to make sure that it only records one meeting, and we don't want to join 2 different recordings at the same time. Then we decided to have a minimum number of idle tasks running at any given time. So let's say we're not really sure how many meetings will be running at this specific time, but what we want to make sure is that we have like a minimum number of idle tasks that can handle like the recordings that users have. So, and another thing we actually did was to have like an auto-scaling module to create or delete tasks due to the ongoing number of ongoing meetings we have. So we know how many meetings are ongoing on our platform, because I mean it's something in our database, so we can easily pull it out and see how many meetings are ongoing. Then we decided to build our auto-scaling module that scales up or down. So it basically creates more idle ECS tasks or deletes idle ECS tasks based on the number of meetings we have. So there's basically like a percentage of tasks that are always ready to pick up recordings. So let's say we have about 100 meetings, and let's say we have about 100 meetings ongoing at this very time, and about 50 of them can be recorded. So for you to know if a meeting can be recorded or not, that means the user is actually paying. So if it's being run by a paying user, then we know that it can't be recorded. So if it can be recorded, then we have to make sure that we get like the number of sessions that can be recorded. So we have 100 sessions that are running totally. Then let's say we have about 70 of those sessions can be recorded. Then we try to make sure that there's a minimum number of tasks. I mean, we're not going to create 70 different instances for those users. It's going to be expensive. What we're trying to do is to create a number of tasks that meets a specific percentage of those calls. So let's say you have about 70 calls, 70 meetings that can be recorded. We can have about 20 different tasks that are ready to take up recordings. And like if we have about 20 tasks that can take up recording, and we have about 70 different sessions that can be recorded, when someone tries to record from one of those sessions, so if someone decides to record and we assign that person's recording to one of those tasks, then we replace that task immediately. So we try to make sure that there are always tasks readily available for people to record calls. And we try to make sure that it doesn't get too expensive. So we scale up or down whenever we need. And we know that there's a specific minimum cost that we have to pay for the over-provisioning, basically. So this is a simple diagram of how it looks. So we have a lot of users trying to record their meetings, and we have a server here. And this server basically handles auto-scaling and also task assignments. You might ask me why we didn't use the default auto-scaling module on ECS. And we couldn't use that because it uses metrics on CloudWatch mostly. So it can help you scale up or down based on a specific percentage of CPU or memory on CloudWatch, and like it scales up or down based on those metrics. But the metrics we had are like the number of meetings we actually have. So we had to build our own auto scaling module that handles it for our own case specifically, rather than using what AWS already had, because it wasn't really going to work for us. We're not scaling up based on CPU percentage. We're scaling up based on like the number of meetings we have. So we have this server that does auto scaling and also task assignments. So when you make a request, it goes to this server. Then this server checks the number of idle tasks that are ready to pick up your call, and it picks one of them and it assigns your meeting to that recording. So at this point, you don't really have to wait for the task to get spun up. The task is already up. All you have to do is start your recording, and this server assigns it to a specific, like any idle task. And if it needs to replace that task, then it's going to create another idle task to replace the one that's already recording. So that's how this works. It has its own auto scaling logic. And mind you, every single one of these tasks here, are AWS Fargate tasks with XVFB, Chrome, Puppeteer, Pulse Audio, and it does the entire recording and uploads it to AWS S3. So now we just go through the pros and cons of that implementation. So the pros are that no dependency on the client side, no joint recordings on one machine, so no video FPS or audio issues. Then the third one is it only takes a few seconds to start a recording, because we actually need to spin up Chrome browser. So that's the only one that takes about 3 or 4 seconds before the recording actually starts. So we're not going through the full 1 minute of trying to spin up an ECS task before your recording starts. So, and it scales in and out pretty quickly when required. And I've already explained this because we built the auto scaling module ourselves. And the only con here is that we're paying a little extra for the idle over provision task. And I guess that's a good trade-off, because we're actually just trying to pay a little more to give our users the best user experience they can get on the platform. Then now we just go through some final learnings and bonus points. So one thing we actually learned a lot and we did a lot of was logging and alerting. When you're building a solution like this, it's very difficult to understand specifically where something went wrong. So if someone reports an issue, it's very difficult to report exactly where it went wrong, except you have some checkpoints in your code base where there are logs, and you try to figure out exactly where the code broke. Because like a lot of the dependencies you're using might have issues, and for you to tell exactly where that issue is coming from, you need a lot of logging and alerting. And alerting is basically what helps us determine what tells us if there's an issue in production. So if a user has an issue with recording, then we'll be the first to be on top of it, and we try to fix the issue before the user even knows, if possible. Then another thing we actually really learned that helped us was locking dependency versions. So, I mean, you don't want to lock dependency versions for all your dependencies. There are some small dependencies that probably need some updates and you can let them update. But there are some other dependencies that even small changes to those dependencies can be critical. And an example of one of those dependencies for us was Chrome. And Chrome releases updates. I don't know the interval at which Chrome releases updates, but at some point we realized that anytime we get really stable in the recordings, then we try to deploy a new version of the recording. And when we're trying to deploy a new version of the recording, then we're downloading the latest version of Chrome, and we start to see new issues. Like the most recent issue we had earlier this year was an issue where audio and video were not in sync. And we're using the browser's media, get user media and media recorder API. So we're trying to figure out exactly where it went wrong. Meanwhile, the only difference between like our stable version and the new version was that version of Chrome, like the latest version of Chrome that we installed. So at the end of the day, what we did here was to lock the versions of some of those specific dependencies. So anytime we try to deploy, we're not downloading the new one. We're sticking with an old version that we already know that it's stable. Then another thing that really helped us was understanding everything that we actually worked with. So we had a lot of dependencies, and anytime someone reports an error, like anytime we see an error, it's always really difficult to navigate to try to figure out, what exactly that error means. And one thing that actually we really learned was that understanding everything you work with, understanding all those dependencies would help you debug faster. So if you have an error with you have an error on XVFB, for instance, you already know exactly where that error is coming from. So understanding these dependencies would actually help you debug issues faster rather than spending days or weeks on a specific issue. And this also led to the birth of one of our tools, our internal tools. So since this solution basically works with Chrome, you're spinning up Chrome and joining sessions as anonymous user and doing the recordings. In WebRTC, if you're building a WebRTC platform, especially on the front end, you want to do a lot of load testing. And that means users joining the call and broadcasting video. You want to see how it's going to work if there are like 100 users broadcasting video at the same time. You want to see if there'll be memory leaks or performance issues. And it's pretty difficult in WebRTC because you need people to join the call. You need actual people to join the call and broadcast video. But since we were able to implement our recording, what we just did was spawn up Lambda functions, put Chrome browsers into those Lambda functions, and we spin up. Let's say you can basically control the Lambda functions to join your call as an anonymous user and broadcast video. So you basically have bots that will join the call and broadcast video, so you can do your load testing or stress testing on the front end, however you want to do it. And one other thing that actually really helped us get to this point was our open-mindedness to different solutions. So we had lots of it took months to get to this point, and we had lots of ideas. And getting those ideas together and experimenting with different ones actually brought us to these specific points we are now. And the last point here is that since we launched the recording feature, we've had about 30,000 recordings, and we've had about hundreds of thousands of recording hours done. So I think that's like a celebration point for us, I guess. And I think that is it. So thank you so much for listening. You have my socials here if you want to find me on like Twitter, LinkedIn, or you want to send an email. But yeah, I think that is it.
Yeah, thank you so much. This was really cool. I really enjoyed this talk. Really enjoyed myself. So thank you. We have a bunch of questions, but I don't think we can go through them because of time. There are some other sessions that are starting now or have started, so we need to go there. But I would say the session is on till like the end of the event. So please just go into the Q&A section of this session and answer as many questions as you can. And I guess people also have, like, you can text Olamilekan directly on this channel, on Hopping, by the way, if you want. If you want to ask a question to him, you can also keep adding questions to the Q&A section, and he would, as much as possible, answer as much as he can. What else? Yeah. So thank you so much. I'm glad you came. So thank you for knowing that.
Yeah. Thanks. All right. Bye.
All right, guys. Thank you. Bye, everyone.